We will start with Christoph Rathgeber, who will do a quick introduction to task 40. And after that, we'll have Gerald Englmair and Fabrizia Giordano, who are also in task 40 and working on it, who will go for some details. You've seen them in the flyers. Well, I think I'm not going to talk too much more. I'll just let Christoph start and take it away, please, Christoph.
Thank you, Jan, for your introduction and for hosting this OnSeminar.
Of course.
I will share my screen.
Mhm.
Mm,
Yes. Uh,
Okay,
wait.
that's good.
I think mine's out now, and yes, you're in.
Here we go. So, as mentioned at first, I'll give a short overview of the completed task on compact thermal energy storage materials within components within systems. So, as those of you who attended OnSeminars before and others also know, a task is let's say, a working group, international working group under the umbrella of the International Energy Agency. Here we worked for 3 years, 2021 to 2024, on this topic. So the scope of task 40 was about compact thermal energy storage materials, and with compact, we refer to two groups of materials. First, phase change materials, PCM. Second, thermochemical materials, TCM. And these materials were characterized, developed, improved, and tested in components, while components refers to heat exchangers and reactors. The task was organized in 5 so-called subtasks, so subgroups that have their respective subtask leaders. One subtask was on material characterization and database. So database, you will hear more details later in Fabrizia's presentation. Material characterization, here we developed guidelines for material testing, for measuring thermophysical properties according to guidelines that can be standardized. Then we had a subtask on material improvement, improvement strategies to tune properties of materials in a way that is needed to successfully apply these materials in applications. Third subtask was on state of charge determination. We will have the presentation by Gerald later on. Then there was a subtask on stability of PCM and TCM, talking about and let's say structuring different degradation mechanisms and processes to improve the understanding of material stability under application conditions. And the fifth subtask, this was really on the interaction between materials and components. It was called effective component performance with innovative materials. Here it was talking about KPIs to characterize, to evaluate components, how to compare different component concepts for PCM and TCM. Now, because it was quite a lot of work, I just picked 2 dissemination highlights, which you are welcome to have a closer look later on. We had a technology position paper published in the solar heating cooling. So I haven't mentioned it yet, but that's an important point. This was a shared collaborative task between the energy storage and the solar heating cooling TCP. And this technology position paper, provides some high-level information on the state of technology of compact thermal energy storage materials, but also systems. It lists a bit about the technologies in the market and gives some actions needed for further deployment of these systems. A second dissemination, also a webinar, where you can watch the recording following the QR code. So here the focus was on material characterization and determination of material degradation. So two topics that we will not cover in depth today. So that can be a bit supplementary to this OnSeminar. Well, the task is completed, so you can also have a look at the final report, which comes in two forms: a short executive summary and the extended final report with the links indicated here. And with that, I'll stop my first part of the presentation, and hand over to Fabrizia first.
Are you able to capture my screen correctly?
Perfect, yes.
Presentation mode? Perfect.
Yes, it's there.
Well, good afternoon again to all the attendees, also from my side. My name is Fabrizia Giordano. I'm a research engineer at the Austrian Institute of Technology in Vienna. And the topic of my presentation today is thermal energy storage materials databases, which has been a topic that has gained attention in the last decades as thermal energy storage technologies has continued to develop. And with them, an unprecedented volume of data has been generated, most of which has been even curated and aggregated into databases and repositories. However, what we still see today is that these resources appear to be, to a certain extent, still fragmented and only limitedly interoperable. And with fragmentation, I do not just refer to the different data types and key metrics which are contained within the databases, but even the methods used to generate this data and how easily we are able to reuse them from one database to another. So in my presentation today, I will address a state-of-the-art review of a total of 30 test databases and really dive into these topics. Then I will present a taxonomy which could be used as a structural framework to characterize the current test data landscape. And therefore, I will address how we can aggregate together similar knowledge domains and if level of aggregations could be distinguished, together with dependencies and relationship between possible database classes. I will then proceed with the domain mapping and address the distribution of the existing test database resources, which we have reviewed according to this taxonomy, and highlight trends, coverage gaps, and possible interoperability opportunities between them. And in the second part of my presentation, I will address the thermal materials database, which has been recently relaunched within the IEA Energy Storage TCP Task 48. And I will conclude providing even an outlook regarding activities ongoing on the database of Task 48. So let's start with the state of the art. And here just a quick message about the distribution of the resources that we analyzed for the review. So we did not just address formal database resources, those having database management systems, but even softwares with embedded libraries, online libraries, or books, as well as database aggregation portals and repository-hosted datasets. This all summed up to a total of 30 resources, which are more or less equally distributed between different thermal energy storage technologies, so sensible, latent, and thermochemical storage. Looking at the purposes of existing test databases, the first one being those resources which provide access to or aggregate existing data. So we are talking about mostly compilation and aggregation of literature data in terms of thermophysical properties, thermochemical properties, just as a possible example, in general, material properties mostly. But they might also contain operational monitoring data as well for more advanced technologies which are already deployed at market level. And a good example of these databases is represented by the NIST Chemistry Webbook Standard Reference Database, and I'll provide a more detailed information in the next slide regarding this resource. Second purpose of existing databases is providing data screening, decision-making support, and benchmarking for the user, so really supporting the user to select best candidate materials based on certain application requirements and constraints. So those databases might usually contain KPIs, both technical as well as economical And a good example is the thermal energy storage technologies dataset, which has been developed within the ECO project. And this is an online tool which is available and really could help you to sort out the thermal energy storage technology which best suits your application, both between sensible, latent, and thermochemical storage, and depending on your requirements in terms of temperature, lifetime of your application, energy density, and other economics parameters. Third purpose goes into the direction of data comparability, and whenever we compare data, we usually refer to standards and protocols that allow us to really compare different data sets. And therefore, these databases do the same and usually go hand in hand with standardized experimental testing protocols or consistent terminologies and procedures in even reporting data and their uncertainties. And a good example is the thermal materials database, which is the one developed in the TAS 48. And I will give more details in the second part of the presentation. Lastly, some databases also address the topic of data generation and prediction and really collect data which go in the direction of novel material discovery, possibly even using AI or other machine learning models, but might also include resources which tend to generate continuous property functions from discrete data sets. And an example is the solid liquid phase change material library, which has been developed at IEA. And this is a numerical-oriented online library which provides computer code for the computation of effective thermophysical properties for around 280 commercial PCMs to date. So I was referring before to the NIST database. This is a really good example of this first category of databases and contains to date around 70,000 species, among which also thermal energy storage materials, and provides thermophysical, thermochemical, and ion energetics properties for these. And as you can see from the example on the slide, also metadata and other important information regarding the molecular structure, for instance, of the materials is available, as well as UPAC or CAS number, or even the chemical structure as mentioned, even in 3D representation. We can also find information such as enthalpy, entropy, or fusion, independent of the temperature. And the methodology used to measure this data is reported, as well as the official reference where this data has been first published. So everything is traceable, and it's possible to go to the original reference too. Now, moving to the taxonomy, as mentioned, this was used in our case to really review the current test data landscape systematically and according to certain classes and aggregation levels. So the first step was looking into the data types and metrics which are contained in test databases to date and try to aggregate them. And so this is what we came up with. First of all, a certain category of data is aggregated at the fundamental level, so to say. So in this case, we talk about data derived from first principle representation of the molecule and their intrinsic properties. Some example of metrics that we can refer to in this case are phase diagram or kinetic models, reaction rates, and so on. If we move to the material level, the metrics change and we look into, for instance, structure, crystallinity, or chemical bonding of the molecule. Usually we look more at the bulk scale in this case, and we might also find thermophysical properties, for instance, thermochemical properties of materials in general. Now moving to the component level, so we have the example of a PCM inside a tank. Then the metrics change again, and they are not just referred to the material itself, but even the integration with possible heat exchanger or, in general, the component. So we find, for instance, energy content, charging, discharging power, state of charge, and so on. And finally, the system level. So we have our PCM storage tank integrated even into a more complex system, possible coupled even to more storage technologies. But in that case, we look at overall system performance metrics under defined operating conditions. It might also include control response time, and other monitoring data. So these are the 4 aggregation levels which we included in the taxonomy. And the next point instead was looking at how this data was generated, which methods are used. And this guided us into a total of 5 different database classes. So let's start again from the fundamental one. In this case, data is obtained from fundamental principles of physics and chemistry. We had the example before of the phase diagram. This can be, for instance, derived from phase equilibrium models. In the case of experimental databases, data is obtained under controlled laboratory testing conditions and defined measurement procedures. So an example for phase change materials in the field of calorimetry could be a DSC characterization to derive specific heat or latent heat of a certain PCM. Correlation-based databases, in this case, data is obtained from either experimental or theory-informed data sets, which are then derived using semi-empirical correlation, or other regression techniques, or even machine learning. An example could be training machine learning models on thermogravimetric analysis to predict chemical degradation of molecules and compounds. The simulation database class is related to data obtained really from physics-based computational models to predict certain material properties. And an example are, for instance, molecular dynamics simulation. With them, we can, as we know, derive several properties, just some example reported on the slide: melting temperature, enthalpy of fusion, and so on. Lastly, the application-oriented class is obtained, in this case, for data derived from field performance evidence. So we talk about mostly monitoring data, but it might also include some techno-economic indicators. So now we have all the pieces of the puzzle. We talked about the level of abstractions, and on the other end, also the database classes. And if we put them together into a matrix, this is what we obtain. So in the epsilon axis, you find the different level of abstraction from fundamental at the top up to the system level. And then the database classes are on the x-axis. And this is the distribution. What you see on the slide is the distribution of our reviewed test databases according to the taxonomy. So what we can notice, the central part of the diagram is the mostly populated one. So at the material level, there has been quite a lot of work done in terms of aggregation of these data resources, and especially thermophysical properties in the case of experimental databases, followed by correlation-based databases. On the other end, what we see at the fundamental level and component and system levels, the resources seem to be scarce or underrepresented. And so the question is, why is this the case? Is this because of limited aggregation potential of data at these aggregation levels, or no need for such databases? This is, of course, an open question, but probably one way to look at this is also the higher level of complexity of aggregating such data resources at this level of aggregation. Since in this case, the variability in the data is not just related to the material itself, but even the component and the system-specific geometries and dimensions, which might differ a lot from one technology to another, from one component and one system to another. So, of course, it's much more complex, much more heterogeneous. And on one end, we find even a lack of standardized characterization methods and protocols in these fields. And now I would like to spend some more minutes about the thermomaterials database. The goal of this database is to provide standard compliant thermophysical data for PCMs and TCMs. This database has quite a long history. It was developed in the previous annexes on compact thermal energy storage, but has been recently relaunched within the Task 48. And Important key highlights of this database: it provides data following established calorimetry guidelines, for instance, for the determination of certain material properties for PCMs, such as latent heat or onset temperatures. User can actively contribute to the database expansion by uploading their measurement, and this undergoes usually a task member review process. Now, I prepared a short video to show you how the database looks like to date. You are able to register yourself as a user, and then when you log in, you will find two tabs, one for the PCM part and the second one for the TCM. If you look at the PCM, we find, first of all, an overview table with key thermophysical properties such as density, thermoconductivity, diffusivity, and so on, and the melting points of the materials as well, of course. It's possible to compare easily at once all the measurements in terms of enthalpies, but even other thermophysical properties, in order to really have an overview at a glance of what is already available in the database. The user is also able to filter out the materials according to specific application requirements or material specification. Here we find, for instance, the material type, the measurement standard, which might have been used to produce the measurements data. And we have filters for temperatures, endothermic heat flow, viscosity, and density. Now we look at one example of a PCM. We find some general information about the material. As you see in this case, we have multiple samples uploaded for the same material, and for each sample, even multiple measurements. This is what we can see from this interactive plotting, which plots together all the measurements at once. We can dive into one of the samples investigated. We find some more detailed comments on the measurement procedure. And the measurement data itself, it's of course uploaded, and it's even directly exportable for the user by just clicking on the link. If you're interested in uploading your data, we have contributed to a step-by-step PCM data upload guide. So here you can find really guidelines on how to upload your measurements data to the database. In the definition tab, instead, you find some information about the calorimetry measurements guidelines, which you can follow to really do your measurements first. In the TCM part of the database, we find, again, first of all, an overview table. Of course, in this case, the properties are different. We look at temperature and pressures for charging or discharging the materials. And of course, it's possible to plot them together as well. By clicking in one of the TCM uploaders, we find again a sample description and a reference link in this case with the diary of the paper, which we can follow to have more information about how the material was prepared in the lab or even measured. And also in this case, we can directly export the data. And the how to use section is available also for the TCMs. So in case you are measuring thermochemical materials, you can also contribute to the database. With that, I will quickly jump to the conclusions. So we reviewed a total of 30 test data resources, and we classified this according to a taxonomy framework. What we notice is that material level data dominate currently the test database landscape, especially in terms of thermophysical properties, most likely because we have more standardized characterization methods already developed in this field, and therefore lower aggregation complexity. By contrast, fundamental component and system level databases still remain limited in terms of aggregated resources. Once more, If you are interested in collaborating in the expansion of the thermal materials database, you're highly encouraged to do so and to get in touch with us. Apologies if you might scan the QR code now. The database is currently, due to maintenance work, unavailable, but it will be made accessible again in the next weeks. These are my references, and thank you very much for your attention, and also to my co-authors and contributors.
Thank you very much, Fabrizia. That was interesting, and this thing looks like it could save a lot of people a lot of work, so to say. Do we have any questions on that? Because I feel like there could be some. Does anyone?
Hello. Yeah, I do have a
Yes.
question.
Yes, please.
From the different type of data, method of like creating a data from Fabrizia mentioned, which type of method is more accurate, or like which type of method is preferred in general? Is there any, or is that depends on the specific scenario?
Well, of course, how to address the quality of data, this is a big topic by itself. Of course, it depends on which data we're talking about, but in general, data containing, for instance, uncertainty for each data point which has been published should be usually preferred. Unfortunately, the practice of calculating the uncertainty of measurement data, but even for simulations, in case certain assumptions have been taken to conduct the simulation, is not always shared in research, but this should be, from my point of view, of course, preferred in terms of data quality. So I think this is, this is
Also,
it.
another follow-up question is, how much impact do you think AI has on like the quality of data in general? Do you think it make it better, or do it add more like interference to it?
AI is for sure a very impactful tool, which indeed will give us the possibility to improve our research. Of course, we always need to question what comes out of AI, and so it depends on the best practices to use AI really for our research. So it's a very powerful tool, but I believe it has to be taken with cautious and questions, so to say.
Yeah. Thanks for your explanation. Thank you.
You're welcome.
All right. There's another very simple question in the chat. When will the website be available?
This is supposed to happen in the next weeks. I cannot give an exact date today, but feel free to reach out to me and to also Christoph Rathgeber in case you're interested in collaborating in the database, and we will give you more information about when this is again available.
What I've planned for this topic, determination of state of charge determination of thermal energy storage, is to have a brief explanation of the already published results we obtained in the IEA Energy Storage Task 40, and also what we're currently doing in the follow-up task number 47. And currently, I teamed up with Louis de Grolier from SPF Ost to coordinate this activity. And myself, I'm from the Technical University of Denmark, Institute for Civil and Mechanical Engineering, where I work as associate professor. So why do we need state of charge determination? Let's start like this. So during the past years, I always noted down some comments. For example, district heating. I heard once, like a CEO said, we abandoned ice storage because we can't control it. Ice storage also a PCM. Many people, when it's about flexible heat pump chill operation, it's difficult when you cannot reliably know what's in the storage to make predictive controls for a day-ahead market. When we talk about high temperature storage, that's also interesting because you assume temperature sensors, you can just do it. But when you're large scale, you need many positions, and it's not inexpensive. So it's also a need for cheaper and more efficient solutions. And for thermochemical storage, simply we need to learn how to actually track when we have different reactants in vessels, what to do. And the system, the system context is in order to integrate thermal storage in a flexible way to make the systems operating to the optimum, we need to have predictive controls, we need to control the power, and for all of this, we need reliable and accurate charge determination. And because of this awareness, this topic can be found across 3 tasks, actually. So there is task 48, where the material scientists are investigating new reactions of the bulk response. In task 47, /solar heating and cooling 74, again, it's a combined task. We are working on the actual methods and prototyping. And we have a relation also to task 46, which is application-oriented energy storage selection for system integration. That's all about controls and how to make storage interacting with the other components. But again, why not just temperature measurements? The answer is for many applications like phase change material, and this is an example from my own lab. We tested like PCM storage. This one is 200 liters extensively in test series, and we found out that the sensitivity of the average bulk temperature, there are 12 different locations we measured within this volume, was, the average PCM temperature was almost the same for 80% of the whole energy content. So it was not really reliable to use that. And therefore, we are now motivated to work with new approaches, which I'll show you in a bit. Important definitions from the expert group. So we define thermal batteries, and this term is chosen with carefulness, is a thermal storage which can instantly determine the state of charge. So an upgrade, you could say, of a thermal storage. Then we can call it thermal battery. It's also the analogy to electrical batteries, where this knowledge is given for nearly all products. And also sticking with this analogy, we are talking about component level properties. So it's not the property of the material, it's about the whole unit, vessel, heat exchanger, and insulation, and so on. And very important, then it becomes a bulk response, and so it's not related to a single piece of volume. And again, what we defined, it's a prerequisite for flexible system operation through thermal energy storage, and it's interacting with model predictive controls, essentially. We also made a research classification because we work in 3 levels. We work with the measurement technique itself, which is basically material science, you could say, like the bulk response. We work with prototyping on the component level, where we compare this measurement technique with external heat flux measurement, and we work with system integration. And to illustrate this, for example, when it's about material response, it's important that it can be reproduced, first of all, and both for charging and discharging of a certain medium. For storage calibration, typically that happens in the lab, either at university or the company, and then you have both the measurement technique and the external heat flux measurement in parallel, with the goal to remove the external heat flux measurement afterwards. And when it's about system controls, ultimately to demonstrate, like we do here at DTU in our CTP Flex project, to demonstrate how state of charge determination can be utilized in interaction with system controls. Well, when we go deep, we won't do it in this presentation, but then there are a lot of other things we need to discuss, do we need a series of local measurements, or can we have, when we have a large vessel, a global measurement? It's about the acceptable accuracy, dynamic response, resolution, and if the properties are the same always, or if there's a certain hysteresis depending on partial load or full load charge. So then it becomes interesting. In 23, we actually, and this is published in the Task 40 report, we performed a survey across the experts with more than 21 research institutions participating. And we found that for PCM, this is on the left side, a lot of component levels / prototype testing were performed, most of them still with temperature, but a number of new approaches being also tested in large scale. For the TCM part, thermochemical reaction, it's mostly work from material labs. The positive thing is a lot of different measurement techniques have been reported, but only a few in the larger scale. And we hope that we get more input in the next years on the larger scale. Some examples on material level. So for PCM, example given from DLR, electrically resistant sensors as a better option for high temperature storage have been tested and demonstrated successfully. So here in different heights instead of ohmic resistor sensors, it has been a different principle. And another example could be chamber pressure, like here demonstrated in a paper by the University of Leiden, where when we have a closed chamber and we have PCM, during the solidification, the inner pressure drops, and during melting, it raises again. So again, there is a measurement technique which can be demonstrated. So that's a proof of concept. But the next step would be to actually build it bigger and relate it to find the correlation to a heat flux. This one is from Austria, where a capacity sensor was built, where the variable of interest is the relative permittivity over the water content of zeolite, absorption material being also used for heat storage to absorb and desorb water vapor. And there is a clear correlation which can be also used in larger scale. And finally, I want to show another example from TCM, this time really like having two reactants. Example given from TU Vienna, they're working with copper chlorides and copper chloride with ammonia, which have different properties regarding optics, UV reflectance, and you can see a different spectrum depending on the ratio of those two reactants. And in this way, just by optical measurements, if you have a reactor where the material is mixed, high temperature, it's about 400 or 500 degrees here, you can optically see what is the state of charge. Yes, based on this knowledge from measurement techniques, we of course need to also, we want to sum up in the current work what is going on component and system level, and also to describe the R&D perspectives. For phase change materials, there are clearly novel techniques emerging, and in every conference I see more and more new results being presented. For TCM and high temperature thermal storage, it's very important to have non-intrusive measurements, so basically being outside of reactors and containers. And there is still a big demand for novel techniques, or let's say like this, to implement the measurement techniques from material level in prototypes. And overall, when it's about data treatment and learning with tests, machine learning techniques are supporting this process, and that's also visible. And just to give you an idea, here is an overview we created about the main principal variables of interest. For sensible storage, it's usually the temperature. Latent PCM storage, it's the phase fraction. For latent chemical reactions, it's the extent of the reaction. And for all of these principal variables, there is a big variety of, we call it proxy variables, or in other words, what you can measure with a sensor. And this measurement can you then relate to the temperature / phase fraction and or state of charge. So an example where you can see both storage development and the use of deep learning methods with artificial intelligence. That's a brand new paper from Bavaria, from CIE. Michael Brütnik explained this also at Euroterm seminar, where he basically applied the sound waves, a set of different frequencies, and piezo receivers. And these raw signals, the ones received, were then used in a neural network to train the model, and later on removing the external measurements, the heat flux measurements, it was possible to actually track the state of charge with this applying of the sound signal. It's still work in progress because it was very small scale and with some limitations, but it is a very promising start. Then I want to go also for a system example, something from our research at DTU in collaboration with partners in Norway and in Germany. At DTU campus, we have now successfully built a pilot storage installation for server room cooling. We have 150 kilowatt hours of storage delivered by Cartesian. And here we are developing, on the one hand side, also with machine learning, predictive controls for ancillary service, so electricity service markets. And on the other hand side, we want to improve the reliability of the cooling system, so some backup for a 50 kilowatt base load small server room. And the way it works is simply say we need to always know exactly which storage capacity we have, and then we need to develop the routines of limiting the thermal power at the right time to charge and discharge to the right extent in the right time, and to make the decisions for 24 hours ahead. Still work in progress, but we have already a lot of practical learnings. And for charge determination, we are doing two things basically. We have some patented device installed in this pilot installation, and at the same time, we are working in the lab to make also realization of novel acoustic methods on PCM bulk response. Something I hope to share with you in a year or two. So coming to the conclusions, we have had a lot of learning and input from more than 20 expert institutions or institutions, 30 plus experts on how measurement techniques can work with direct material bulk response. And state of charge is a component level property, and we need this for flexible system operation. And currently, we are looking for more contributions, so you can reach out to us if you have some research or some new development you want to share. We are looking actively for more system integration examples. Also, it is very interesting to track how AI methods can be used to support this, both R and D. And the focus currently is, that is our impression, for phase change materials, there are more and more sensors applied and more pilots installed. For TCM, it's going from material research to the prototyping level. And for high temperature tests, I think, a lot of innovations are needed, and they are urgently needed. So if you work with that, I would be welcome to have a chat with you. Thank you very much.
Thank you, Gerald. Also, you were absolutely right. That was not as complicated as I imagined at first. Just a lot, but not very complicated. Just a lot of work in it. And if anyone wants to, has some good ideas for high temperature measurements, then please call Gerald or write him. Any questions on that? Anything anyone is interested? Or was it just too much?
A question. What's the best way to reach out to you, Gerhard, if I have more ideas I want to share in the future with you?
I mean, you can always write me per email.
Email?
That's the quick way.
What's your email address? Is it posted somewhere
Can you
or?
see it here?
Oh, yeah, I can
Hearing.
see it.
Yes.
Thank you.
And
Appreciate it.
in general, I mean, we can also investigate if you could become an observer or participant in the task if you write me, and then we can involve also Christoph for this.
Okay. Thank you. Appreciate it.
All right. Anyone else? Anything else? If not, then I would hand this right back to Christoph Rathgeber, who will probably also be taking over the part of Beatrice Schulz and make a little introduction of I think Christoph has shared his screen.
Yeah.
That is very nice. Thank you very much. And yeah, as you can see, first of all, something about task 48, and then we will see how this goes on. Christoph.
Yes,
thank you very much.
thanks again, Jan. So yeah, there are many tasks, many task numbers. Now we heard a lot about the task 40 and also parts of Fabrizia's and Gerald's presentations and the work are continued in the new tasks on thermal energy storage materials and components. I would like to take now a few minutes to introduce both tasks and then show one slide where you see also an overview of the next meetings where you, those of you who are not yet part of it, could be involved in person. So the first of the two new tasks is thermal energy storage materials. Again, a collaborative activity between energy storage and solar heating cooling TCPs. The scope is similar like in task 40, but with the addition that we now also look at sensible heat storage materials, well, excluding water. So could be both on the high temperature side, but also for sub-zero applications. And the activities in this task are about materials, characterization, development, and synthesis and production. So again, we have several subtasks. The first one is called lessons learned. Here, our focus is, as it says, on the dissemination, on the discussion of lessons learned from previous tasks, some examples you heard about, but also the things that we learn and want to communicate in the two new tasks. And the figure here shows the title pages of the four final reports of the previous phases. So this is really a long-lasting activity with lots of experience gained for all involved, and we want to put more focus on delivering certain key learnings to the outside. Then we again have a task, a subtask on material characterization. Again, it's about developing measurement guidelines through round-robin tests. Here you see a list of thermophysical properties that are currently being worked at. So it's thermal diffusivity, conductivity of PCM, then thermal conductivity at high temperature, solid density of TCM, degradation via TGA, specific heat capacity at high temperature, and viscosity of PCM. And so for all of these topics and properties, there's a group of experts with one coordinator who work on developing these guidelines by measuring the same material, comparing results, improving the procedures, try to get a reduction in deviation between the different measurement results, exchange experience with the handling of materials, the elevation of data, how to accurately determine the uncertainty in measurements. So these are the topics that you can join here. Then we have one subtask on material development and production. Here it's about systematic development of materials. So systematic means that you have an application with a certain requirement for a thermal energy storage material, and now it's about translating this requirement to design targets for materials. Then a big part of work is done in terms of exchanging knowledge and best practice about synthesis and production of materials from waste, byproducts, using sustainable resources, etc. And the third topic, upscaling materials production. This is something that is usually being done in collaboration with industry, and we also want to exchange ideas here. The subtask on the thermal energy storage material database, well, this continues to what Fabrizia showed. There's also the plan to create and add a wiki with relevant terms and definition for thermal energy storage materials here on this website. So you can find out more by checking out the two websites, one on the energy storage TCP side, one on the solar heating cooling. The second task, so this time we really split up between materials and components. So the second one is obviously on components. I will introduce this on behalf of Wim van Helden, who is here the task manager for the solar heating cooling program. Scope here are thermal energy storage components with challenges in their design. So two groups again, heat exchangers that are relevant for PCM and sensible heat storage materials, and then reactors in terms of thermochemical materials. And the components are strongly determined by the applications behind. So different applications are included, from small to large capacity, from small to large power, and also ranging up to high temperatures. On the right, you see some images for the design and for applications. So this is really in close collaborations to companies being active in the field of thermal energy storage systems. Objectives of task 7447 is to bridge the gap between materials and the practical implementation. So the component is exactly this bridge. And the three key pillars which are worked on in the subtask are first, application-oriented case studies, so a collection and analysis of these case studies. Then talking about component design and integration. And the third subtask, already presented by Gerald, is the topic of determination of the state of charge. Here again, two websites for your further reading. And now the promised slide on the next meetings of these two tasks. So it's two tasks, but it's one group sharing these meetings. The first one, it's not a classical task meeting. It's the task group organizing an industry workshop in connection to the Eurosun 2026 conference in Freiburg, 14 September, the day before the conference. The next classical expert meeting, the third expert meeting will be in December, as you see here, connected to a thermal energy storage workshop that is organized by SINTEF in Trondheim, Norway. And the third bullet point here, you see the dates of the fourth meeting in May next year, Ljubljana, Slovenia. This will be in connection to a TCM summer school. It will be the second edition. The picture here shows the last year's edition. So if you are interested in joining this activity, please get in touch. You see here the opportunities to meet and exchange with the experts in person, but there are several other occasions, also online meetings to more specifically work on the subtask objectives in between. That's it from my side related to all these tasks on thermal energy storage materials and components. With this, I will stop sharing.
Thank you very much.
So it would be now time for some questions, and then if Beatrice has not joined, we'll say a few words on the application-oriented energy storage selection task.
Right. So any questions on this, overview that, let's see if there's any questions about that. Possibly not. Probably didn't bring up too many. All right, since nobody's asking, then Christoph, just go ahead and tell us a bit about task 46.
Yeah, so yes, thanks. So task 46, APES, it says application-oriented energy storage selection. So what is it in it? What's in it? So the idea and the goal that we want to reach with this is to have a matchmaking process, finding matches of applications and energy storage systems technologies. And so the starting point for us here is looking at the demand side. So that means what is the actual demand in a certain application? The demand can be heat, cold, drying, whatever. And then with this specific demand, we want to we want to match this with a energy storage technology that technology-wise, but also economically fits. So these are the matches we want to derive. And building up on that, we want to come up with a list of matches that are most relevant for the energy transition. So we will also have an evaluation of these matches in terms of their impact economically, and also their potential, let's say, energy savings, their potential CO2 mitigation potential. So this is being worked at in the task 46. Similar as the two other tasks presented, task 46 has been operated for 1 year, so there are 2 more years to come. It's not too late to join. That's the message. So if you are interested in this activity, which is not that deep into certain technologies, materials, components, but more on this matching applications and systems at a higher level. If you're interested, again, feel free to get in contact with me, and I can connect you to Beatrice Schulz of BWS and the relevant people behind the task.